most people are here. Some are coming in later. The time is already 8:30. Let's better get started. So our first 2-hour lecture today will be given by Professor Kyung-Jin Lee from KAIST, South Korea. Professor Lee is actually a long-time expert in the field of spintronics in terms of theory. Personally, I enjoy reading a lot of his theoretical works on spin torque, SOT, STT. And today he's going to give you, for the first part, he's going to give you a simulation and theory on magnetism. And for the second part, he told me that he's going to talk about some of his recent research. So without further ado, let's welcome Professor Lee.
Thank you. My first part is really boring, I think. So that is for various methodologies to simulate the spintronics and magnetism steps. So first of all, I will give a brief introduction of why we need simulation and theory. Then I will explain various approaches for different problems in magnetism and spintronics theory. Okay, so this is your experiment. There are many unknowns in experiment. We do not know what is exactly inside. However, I think it is always true. Even though you make a mistake, if you make the same mistake in the same environment, then you would have the similar result within the statistical error bar. In contrast, the theory is based on the assumption. You may have different theories, elephant, camel, polar bear, and then you may discuss with the experimentalist to check, please exclude camel by measuring this, or polar bear, and so on. One thing that we have to be careful is that the theory is not always correct, because it is based on the assumptions. So you have to be very careful to check if the assumptions used for that theory works for your experiment. And numerical modeling is located in between, so that connects the experiment with theory. So it is less black box than experiment. We know what is going on inside, but it is more black box than theory, because theory gives the very simple analytical expression sometimes, but the modeling gives just the numbers. And also you can make mistake in your code. So plus, minus, divide, division, and so on, okay? So you have to think if your numerical results are reasonable or not before reporting that. Okay, so the first one is the mean field theory. Here we want to calculate the magnetization as a function of the temperature. Two different viewpoints. One is the classical viewpoint. In this case, your magnetization vector summarily fluctuates around the preferred orientation along the magnetic field direction or magnetic z-axis direction. Then the average n component along the preferred direction decreases with the temperature, and you can calculate that. In the quantum mechanical viewpoint, your angular momentum state is state quantized, so occupation probability of each state depends on the temperature. Then you can calculate the thermal average of this angular momentum along a specific direction that also decreases with t. And mean field approximation means that you assume, you consider the effective magnetic field acting on a spin S sub I. Here I is the lattice index. And then that is corresponding to the thermal average of S of all neighboring spins. For example, you can use that for the exchange interaction, exchange field, based on the Heisenberg exchange interaction. And with the thermal average spin this S, you can define the small s. This is the fluctuation, which is the difference between the real local spin and this ensemble average. Then you can put these two into the above equation, and finally you arrive at this equation. The first term is, describes the fluctuations, so usually we ignore that, because that is small. And the other terms are all related to the local spin S. So you can define the mean field, mean exchange field by taking the differentiation other terms with this vector S. Then, by multiplying lambda G factor and Bohr magneton, then you can calculate the magnetic moment. And in this case, this ensemble average is given by this Brillouin function with the total angular momentum J. And so this magnetic field B also contains S here, and therefore this equation can be solved only iteratively. Here is an example. This is for the Wales transition metal ferromagnet. So RETM, such as gadolinium cobalt. Here are parameters that I have used. So for the exchange interaction, TM is largely positive, Wales is positive but small, and TMRE is, I took the negative value to describe antiferromagnetic coupling between cobalt and gadolinium. They have different angular momentum and they have a different lambda G factor. And this is the calculation result based on the beam field theory. So you can find that the blue curve, that is the net magnetic moment of this alloy, has zero value far below the Curie temperature. And this temperature is known as the magnetic moment compensation temperature. And that arises because there is antiferromagnetic coupling and RETM element have different temperature dependence because of the different interatomic exchange interaction. So next one is the Monte Carlo method. Here we want to flip a spin depending on the probability. And the most widely used algorithm is Metropolis algorithm, consisting of these 6 steps. The first, from a state, which means the spin configuration x0, the next state x1 is generated with a single spin flip. How? You calculate the energy difference between these two states and calculate the probability P based on this equation. And then you independently generate the random number R that ranges between 0 to 1 and compare this R with this P. If R is smaller than P, then you can accept. It means that you flip the spin. However, if R is larger than P, then you reject the spin flip and instead stay at the original state. And you repeat these steps from 1 to 5 until your own criterion is satisfied. Here is an example that is for the exchange bias. So here we model ferromagnet and anti-ferromagnet with an interface, and we were interested in what is the effect of the interface mixing on the exchange bias. So here R means the number of FM spins to the number of total spins at this interface layer. So if R is 0 or 1, it is the perfect interface. If R is 0.5, it is the maximally intermixed interface. And here is the result. When R is number 1, then I got this kind of hysteresis loop, and you can find that there are some exchange bias, but not very significant. But if R is close to the 0.5, then you can clearly observe the exchange bias. The reason is there are some formation of the antiferromagnetic domain or associated ferromagnetic domain at the interface, depending on the intermixing degree of freedom. So next one is micromagnetics, which is I think most widely used in the magnetism and spintronic study. So this is kind of a standard tool to study the magnetization dynamics. So we numerically solve Landau-Ricci-Gilbert LLG equation for many interacting magnetic moment, and the equation is here. And tau is torque other than precession and the damping torque. It can be spin transfer torque or spin orbit torque or magnum torque, summer torque, and so on. So for the precession torque, we are interested in the spin dynamics, and therefore we calculate this Heisenberg equation with the spin operator S and the relevant Hamiltonian H. So with this Zeeman type Hamiltonian and using this Pauli spin matrix, you can arrive at the time dynamics of the spin is given by gamma S cross B. then you replace it into the magnetic moment, and you can arrive at the famous precession torque. And this precession torque originated from the Zeeman-like coupling between the spin and effective magnetic field. For the damping torque, actually we have to follow the same procedure. In the Hamiltonian, we have not only Zeeman type term, but we also spin-orbit coupling, electron phonon, and so on, so on, so on. So there are many more terms. However, usually it's very difficult to solve this equation of motion for the spin, including all these interactions with the environment. So instead of solving that, we just take very phenomenological way to look for what is the direction of the damping torque, based on the fact that damping effect must give the energy dissipation. So you calculate the energy rate that is given by m dot b and time derivative. It must be smaller than 0. It means that your damping will decrease the energy. Then you can find out that in this constraint, because of this constraint, damping torque must have the form of m cross d and dt. And then this Gilbert or Lambda-Lipschitz put just a phenomenological constant alpha here, because we don't know what it is. And then we pick this equation, resolve with the experiment, and find out what is the alpha of your sample. Okay, and there are effective fields. It includes exchange, anisotropy, magnetostatics, Zeeman, and many more things. And here, this table shows what is the relevant energy density for each term and what is the origin. So exchange comes from the Heisenberg exchange, anisotropy comes from the spin-orbit coupling, with difference in the orbital quenching depending on the magnetization direction relative to the crystal orientation. And the magnetostatic field comes from the magnetic dipole attraction, and Zeeman is simply the exchange field, external field. So when we use the continuum model, exchange is given by second derivative of m, and uniaxial anisotropy is given here, where k is the direction of the EG axis. And dipolar interaction actually has a little bit complicated form because this is long-range interaction, and the external field is given here. So the other terms are all local or uniform in most cases, but dipolar interaction is non-local, and which means that here that there are two terms. One is the divergence m, that is the volume charge. And the other one is m and that m. And n is the surface normal vector of your small cell. So that is the surface magnetic charge. So the magnetic dipole interaction tends to remove any volume charge and any surface charge if the situation is allowed. So for example, I think you know all about this, but so for example, if your magnetization is in the single domain and your sample is in this shape and magnetization is in this direction, then you can convert this one to kind of magnetic charge. Here I have a plus magnetic charge because magnetization was non-zero here but zero here. So there is a spatial gradient to the magnetization. And you can also define the negative magnetic charge here. Then you forget about the magnetization, but simply following the electricity idea, okay, my field start from the positive charge and at the negative charge, which means that this field is always in the opposite direction to your magnetization direction. That's why this is called the demagnetization field. And you can do the same thing for a different magnetization orientation. Here you have a positive charge here, and here minus negative magnetic charge there. Then you have a magnetic field along the thickness direction. In this case, the retro length is much larger than the thickness, meaning that this field magnitude is much larger than this one. In other words, this acts like the hard axis field. The other important effective field is the thermal fluctuation field. So we want to incorporate thermal fluctuation in the LNG equation. Then what we do is we add the thermal fluctuation field BTH to the effective field, from the fluctuation dissipation theorem, this BTH must satisfy this condition. So each average in time and the space must be 0 because it must be random. However, when you multiply these two, then you have the delta function, meaning that the magnitude of this field depends on the damping and the temperature and your magnetic moment. So fluctuation dissipation theorem means that if you have any kinds of source of the fluctuation, there must be the same magnitude of the dissipation. They must be balanced. If not, your system cannot go to the steady state. That's why you have a damping here. So at the zero temperature calculation, you have very clear recession and damping, but when you add thermal fluctuation field, then you have additional random luck around the original trajectory. Okay, then how to numerically solve? We usually discretize your sample into the uniform cells based on the finite difference method. But of course, there is a way to do that with the finite element method where you can use different shape, okay? But this is more widely used. So you have the equation, and this equation must be satisfied at all of each unit cell. And here are two main assumptions. One is that your magnetization is uniform within a cell. And the second assumption is that we use the continuum approximation, meaning that your magnetic field, actually this is the continuum version of the exchange field, and that is discretized in this way, where D is the unit cell length. So I will talk about a little bit about these two main assumptions. The first one is M is uniform within a cell. And because of this assumption, your simulation result becomes invalid near the Curie temperature, because at the Curie temperature you actually excite high K magnons, and the wavelengths of the magnon can be smaller than your unit cell size. So actually it violates this first assumption. A representative example was given in this very nice paper. So in this paper they have tested, so they solved the LNG equation for the magnetization versus temperature. So we just used this assumption, then they got this result for cobalt. So you see that the Curie temperature is 10,000 Kelvin, which is too much overestimated because of this assumption ignores high K magnons within a unit cell. So these authors propose a proper normalization concept depending on the cell size and the temperature. So the exchange is normalized, renormalized, and all other terms are also renormalized depending on the temperature, and they got this result. So now TC is around 10,000 K, which is quite reasonable. So one notice here is that actually this normalization is a little bit complicated. So it's difficult to apply to many problems. So please try avoid to calculate the magnetization dynamics near the Curie temperature using the conventional micromagnetic simulation. The second assumption is this continuum approximation, meaning that unit cell size times the gradient of the magnetization is a small parameter. So if this assumption is invalid, then your result becomes very, very crazy. Okay, so there is a criterion for ferromagnet. So your unit cell size must be smaller than the square root of the exchange energy and the anisotropy energy or dipolar energy. And that is typically a few nanometer. If you are working on the strong perpendicular magnetic anisotropy sample, it can be even 1 nanometer, which means that if you use the 10 nanometer cell for the calculation, then the result becomes unreasonable. Okay, So for the ferromagnet, we can define this length scale. For the anti-ferromagnet, there is no way to define this length scale, so you have to go to the atomic lambda equivalent equation. So what can we do with micromagnetics? We can do many things when two assumptions are fine. So here I show several examples, including the spin torque induced precession, spin wave attenuation control, spin wave propagation in the presence of the velocity Fourier interaction, and very briefly droplet creation in the presence of DMI. Okay, so in this work, we added the spin transfer torque one term, so Slonjarsky spin torque in the LLG equation, and check compare the numerical result with the experimental result reported in this paper. That was the first report about the spin torque induced magnetization precession. And this is the experimental result, and they plot kind of a phase diagram depending on the injected current and applied magnetic field. And this region is hysteresis region. P and AP both are stable. Here AP stable, P stable. Here there is a large angle precession, and there are some weird region. That's why they named it W, because they couldn't understand why this region appears. And actually, this weird region is related to the lines. For example, let's see, for example, this one. And you see that the frequency range runs from the 2 to 18 gigahertz, and then you can find the line is a few gigahertz, which means that the dynamics is highly invariant. And they also compare this experimental phase diagram to the macrospin theory based on this equation. And yeah, the quantitative difference is okay. However, they couldn't observe this weird region here, and also there are some differences in the details. So we did LLG study. This is our result, and let me compare this one to the experiment. So here, not switching, and we observe some W region here. And actually, in this W region, we calculate the modulus of the magnetization of a whole sample. And if it is single domain, it must be very close to 1. How do you see that it is far below than 1, and sometimes it's close to 0, meaning that your magnetization configuration is highly nonlinear and complicated because of the spin wave excitation. Second example is the spin wave attenuation. In the continuously varying the magnetization, the shape of the spin transfer torque changes a little bit. So now we have an adiabatic torque proportional to the gradient of the magnetization, and non-adiabatic spin torque, including the gradient and also a factor beta. This beta term is called non-adiabaticity of the spin current. That characterizes your spin current spin polarization doesn't follow the magnetization direction for some reason. And concerning the first talk, there was a very nice work, experimental work on the spin wave Doppler shift. So they measure the frequency of the spin wave depending on the direction of the current, and they observe this delta F. So it's very similar to the Doppler shift. Then what is the effect of the non-adiabatic spin torque? Because Doppler shift comes from the adiabatic spin torque, and we studied that, and we obtained the result that actually this beta term, non-adiabatic torque, controls spin wave attenuation length. So this capital lambda is the spin wave attenuation length that is proportional to the wave number k, and inversely proportional to the damping and the frequency, but there are some correction term due to the non-adiabatic spin torque. So when this beta U0k is same to the alpha omega f, when you apply a large current, then lambda goes to the infinity, meaning that it can be negative. Okay, if this is larger than this, then you can actually amplify your spin wave amplitude depending on the distance from the spin wave source. Because non-adiabatic spin torque compete with the damping torque in this situation. Another example is the spin wave propagation in the presence of the DMI. And as you know, DMI is the anti-symmetric exchange interaction between neighboring spins and characterized in this formula. So it favors to make the S1 and Sj, so Ij spin direction to be perpendicular to each other if it is allowed. And if it is counterclockwise, clockwise, depending on the sign of this DMI vector. So we first derived spin wave dispersion, including this DMI, and found that DMI correction appears in this way, so it is proportional to K, so linear in K. And then we checked that by comparing it with micromagnetic simulation. Here symbols are micromagnetic simulation, and the line comes from this equation. So you see that the frequency versus the wave vector curve, if you have non-zero DMI, your dispersion curve shift to one direction depending on the sign of DMI, because this gives the linear in K contribution. And which means that if you fix your frequency and measure K, or you fix the K and measure the frequency, and when you find this delta F, you can quantify your DMI from your sample. And this is widely used to measure DMI in various papers. Okay, and the other one is magnetic droplet nucleation in the presence of DMI. So here what we have studied is that we have a very wide sample, and there are some reverse domain nucleation in the presence of in-plane magnetic field. If there is no DMI, there is no difference in terms of the energy for this side and that side. However, if there is DMI, DMIs always want to make a chiral structure, but the in-plane field favors one of these two, so it distinguishes these two domain walls in terms of the domain wall energy. And then you can get this nucleation field that is different depending on the DMI. So the experiment has been done, and numerically we wanted to find what is the saddle point or the energy barrier for the right domain wall and the left domain wall. So when you use the micromagnetic simulation, you usually try to find energy minimum state. Okay? When you run the LNG equation for quite some time, it goes to the steady state or it goes to the energy equilibrium, meaning that low energy state. But in this case, we wanted to know the energy barrier, meaning that energy maximum. Okay? So here we used the NEB method, Dutch elastic band, but it was widely investigated in the chemical bonding studies. Then we can calculate this kind of curve depending on the configuration of the spin. Then we can numerically obtain the energy barrier depending on the in-plane field and the DMI and so on. And then we got this kind of result. Okay? And it gives a very good agreement with the experimental result. Next example is the atomistic energy. I have told that we need atomistic energy in order to study the antiferromagnetic or antiferromagnetic coupled ferrimagnetic dynamics. So all the things are the same, but we just do not use continuum model. We just follow each spin at each lattice. Okay? Then we just use the same equation of motion, but now this spin is not the approximated one from the continuum model, but that is exactly the atomic spin at that lattice site. So, for example, we have studied the antiferromagnetic domainal motion induced by the spin-orbit torque. We first derived domainal velocity, shown here. So B sub D is proportional to the magnitude of the damping light torque, and that is inversely proportional to the damping constant. So if this analytic formula is correct, the dominant velocity must be linear in the current because B sub D is damping like to meaning that it is linearly proportional to the current density. And here, this red line comes from this equation. This is just linear as a function of the current density. However, this blue dot, the red dot, were obtained from the atomistic LNG simulation for the antiferromagnetic dominant motion. You see that when the current is small or the dominant velocity is small, it is well described by this equation. However, when the velocity approaches to some value, then it cannot follow the linear relation, but instead it saturates. And then we found that the antiferromagnetic system mimics relativistic dynamics, which means that we have some range vector correction here, where lambda is the dominant width and lambda EQ is equilibrium dominant width. Then when we include this range vector relativistic correction, then we obtain this dotted line. So it describes the numerical result reasonably well. Then we also check if the dominant width indeed shrink depending on the dominant velocity. Symbols modeling line is this equation, and it exactly describes this range contraction of the dominant width. Okay, so next example is the field-driven dominant motion in rare earth transition metals ferromagnet. And as you have seen before, we have a rare earth and transition metal. They are antiferromagnetic coupled. Because of the different longitude vector, the magnetic moment variation and angular momentum variation are different. As a result, for the net magnetic moment, you have this temperature where net moment is zero, which is called magnetic moment compensation point. However, at a different temperature, your net angular momentum is zero, so that is called angular momentum compensation point. So now you may be curious about which point is corresponding to the antiferromagnet. So if you are interested in the straight field, Tm is antiferromagnet. But if you are interested in the dynamics, then Ta is the antiferromagnet, because dynamics is described by the angular momentum, not by the magnetic moment. So we have derived field-driven ferromagnetic dominant motion equations of motion using the fieldless approach, or called the two collective coordinate approach. Here we use the dominant position x and dominant angle phi as variables, and then we arrived at these two coupled equations of motion. There are many terms, but in this part the important term is g here, which is called gyrotropic coefficient. So actually this gyrotropic coefficient is proportional to the net angular momentum, which means that when your temperature is at the angular momentum compensation temperature, then this net angular momentum becomes zero. In other words, G is zero. So you drop these terms. Now you see that the first term only affects X. So it is used entirely to move your dominant without rotating your dominant, because now your X and phi are completely decoupled. So using these equations of motion, we can derive dominant speed. For example, field-driven one in the precessional regime is given here. So here you have magnetic field, because we derived the dominant motion by external magnetic field. And then there must be M1 minus M2, because magnetic field couples to the net magnetic moment. But interesting point is that delta S, that is the net spin angular momentum, appears in the denominator with a squared, which means that if at TA delta S is zero, but M1 minus M2 is non-zero, so we may expect dominant velocity probably be maximized at the angular momentum compensation temperature. Okay, so the experiment has been done by Taro Ono's group Kyoto University. They used iron cobalt gadolinium, and they fabricated this kind of sample. They first applied the uniform magnetic field to saturate that in one of the direction, and then they applied current here, and because of the worsted field, it creates the domain wall. But in the presence of the magnetic field, it moves to here, and they measure the almost whole voltage in this whole bar structure in the time domain, so they can know what is the time taken for a domain wall to move from here to there, and they know the distance, so they can calculate the domain wall velocity. They first measure the magnetization compensation temperature. That can be easily done by measuring the almost whole resistance versus magnetic field along the z direction. So here it is clockwise, and the hysteresis becomes very large, and then the switching direction polarity is reversed. Actually, this is corresponding to the Tm because here magnetic moment, then magnetic moment is very small, meaning that you need very, very large field to switch your magnetization. So here, coercivity is flat. It goes up here and then decreases. So this temperature is the magnetization compensation temperature of this sample, which is around 220 K. Then they measured the domain velocity using the method that I have explained before at different temperatures and summarized the result here. They observed that domain velocity becomes very large at temperature of 310 K, which is very different from the magnetization compensation point. Okay, so then they ask us why we have a large domain velocity at this temperature, not here. So we did theoretical and numerical study. For this one is the numerical study based on the atomistic energy equation, and the result is summarized here. So we varied the net angular momentum delta S, and we found that indeed domain velocity maximized at zero net angular momentum of the system because, as I showed before, delta S appears in the denominator and the square term. So when delta S is zero, then this becomes maximized. Okay. The other example is for the magnetic fermion. As you know well, there are a lot of studies on magnetic fermions because it's small and probably fast and topologically protected a little bit, not perfectly. So one of the issue in this magnetic fermion dynamics is the fermion Hall effect. So in this experiment, they generate a single bubble or magnetic fermion and inject the current along the horizontal direction, and then took these images as a function of time, I think. So it moves along this direction because the force is along that direction, but at the same time they observe there is a transverse motion just like the Hall effect, and they name that as the fermion Hall effect. So actually, this fermion Hall effect can be well understood by using the concept, familiar concept with the charge Hall effect. Charge Hall effect arises from the Lorentz force, where Q is electron or whole charge, and R dot is the velocity, and B is the true external magnetic field. In case of the fermion, there is no true charge, but there is a topological charge defined in this way, where n is the magnetic order parameter. And there is no true magnetic field, but there is a fictitious magnetic field that is proportional to the net spin density. So from this description, you can immediately recognize that if you remove this net spin density, then there will be no fermion Hall effect. This idea was first proposed by these two theory papers. They have studied the